Good morning, all. In the last session, we started with this unit number 4, that is processing of powder metals, or commonly known as powder metallurgy. We started with introductory part, and then we discussed this uh, process that has to be followed whenever you produce any part using this powder metallurgy technique. So the process is going to begin with the metal powders. We mix some additives, lubricants, and all into that metal powders, and that mixing of all those things is called as blending. And once that mixture has been prepared, the next step will be offering the shape of the product. It's like offering shape to a wet clay. And the techniques that are used to offer initial shape are called as compaction techniques. The compaction techniques are going to be categorized into two: cold compaction. From name itself, we can easily get that it is being conducted at atmospheric condition. And second one is hot compaction, that is carried out at certain elevated temperature. And once you have given the shape to the product, the part obtained is called as green part, and that would be further processed using sintering technique. So sintering is basically heating that part to a certain temperature. That temperature range will be dependent of the metal powders that are being used or raw material. And at that elevated temperature, the additives, lubricants, and some binding materials that you have mixed into metal powders, these additive lubricants and binding material will melt and form bonding with the metal powders. And at the end of sintering, you will get the final product with the properties that are better compared to the green product, the product that you have obtained after the compaction. When you further process or when it undergoes sintering, the properties are going to be enhanced. And in many cases, that product need to be processed further to impart some surface characteristics or to impart some dimensional tolerances. And the techniques are secondary and finishing operations. So this is going to be sequence of operation when you want to convert a powder metal into a product. So these are the series of operations that we need to follow. After that, we discuss the shapes of the metal powders. These are the various shapes available. Then obtaining techniques or techniques that are used to obtain the powders from the raw metal. So there are various techniques that you can use to obtain the metal powders. And we started with the atomization. We know that atomization has got four categories. Like when gas or air is used as a working fluid, when water is used as a working fluid, or when that molten metal is uh, allowed to fall on a rotating disc, or in the last case, the rod or metal rod will be heated up to melting temperature and same will be rotated with a high speed, so that that melting end will continuously gets converted into metal powders. And all these techniques are part of atomization. So this is first method that is used for the production of metal powders. Then second, we discussed a reduction. It is basically a chemical reaction where the metal oxides will be reacted with certain gas at a certain temperature, and there will be purification of the metal powders. For example, here is a copper oxide that is heated with hydrogen gas, and on heating, this H2 will react with O. You will get a water molecule, and this Cu, that is copper, will be separated from that oxide. So you will get a pure copper. The next technique was electrolytic deposition. So putting that raw material into a electrolytic solution, and two electrodes will be immersed in that tank. One would be connected to positive terminal, another negative terminal, and because of that one, the metal that you have placed into the electrolyte, it will be separated into positive and negative ions, and those ions will be attracted towards the opposite electrodes, and that way you will get the pure metal. Then next one is formation of carbonyls. So when you get the carbonyls, on decomposition, that carbonyls will get converted into pure metal. Then next was comminution. Comminution was having three types again. First one was crushing, second one milling, and last one is grinding. All these has been shown over here that we have discussed. After looking at the sketch, you will remember what we discussed in the last session. Then last one is mechanical alloying. Mechanical alloying is nothing but the ball milling itself. But instead of putting single powder into the milling chamber, there will be multiple powders inserted into this milling chamber, so that all these particles will diffuse against each other, and you will get a alloy metal powder. Okay, so mechanical alloying, from name you can get that it is forming the metal alloy powders. Then after that, we started with the, I think this one also we discussed in the last session, particle shape, size, and distribution. The first part we started with the particle size. So to identify the particle size, the similar technique is used that we have seen in abrasive machining processes, that is based on the mesh size. Mesh is nothing but the number of openings in the particular area. So if you increase the mesh size, the particle size is going to be decrease, because in the same area, if you increase more number of openings, means there will be a smaller particle that will be passed through those openings. So that way, increase in mesh size is nothing but decrease in the particle size. That same we can see over here. If mesh size is 30, particle size is 600 microns. If mesh size is 100, particle size is 150 micron, and when mesh is 400, particle size is 38 micron. So increase in mesh size is nothing but the decreasing in decrease in the particle size. Then there were certain techniques that were used to identify the particle size. First one was sedimentation, then microscopic analysis, light scattering, then optical methods, and suspending particles into liquid, and identifying their electrical characteristics. All these things we have discussed. In the first one, sedimentation, we put powders into a liquid, and we know that if you put those powder in some liquid, a smaller particle and larger particle, smaller particle is going to take longer to settle at the bottom, whereas larger particle will settle down quickly. So time taken by that particle to settle down will be used to identify the particle size. Similar, then microscopic analysis is there, light scattering. Uh, Laser will be allowed to fall on the metal that powder particles, and scattered light will be absorbed through sensors, and that will be utilized to identify the particle size. Then optical methods, that is, on the one side there would be light source, another side there would be a sensor, and when powder is passed in between those two, the obstacle created by that particular particle will be utilized to identify particle size. So these are the various techniques that also we have discussed in the last session. Now today we are going to begin with particle shape. We were about to start this one, so today we'll continue with this point, particle shape. So particle shape, there are two characteristics that are associated with this particle shape. The first one is called as aspect ratio, and second one is called as shape factor. Aspect ratio means if I take a cylindrical rod that has got small d diameter and L length, okay, so when I take a ratio of those two dimensions, it has got two dimensions, there might be a three dimensions also, but what we need to do, a ratio of largest dimension to smallest dimension. So for this rod, if I take D and L, so that has to be L by D, and this ratio is nothing but the aspect ratio. This is going to be a commonly used term, and this term is going to be useful in uh, multiple subjects. So this term might be known to you already. If not, then remember this one. Aspect ratio is nothing but the ratio of largest dimension to the smallest dimension. And if I consider this rod, that ratio will be L by D. Okay, so basically this ratio indicates the slenderness of the workpiece. Slender workpiece means a thin workpiece that has got a large length. That kind of object we call a slender workpiece. Okay, so this L by D or aspect ratio indicates slenderness of the workpiece. So this is first characteristic associated with the particle. If I take a particle of some random shape, then I will take one dimension. If it is a square, circular, or any kind of, then I will take one of dimension that is supposed to be a smallest one, and another dimension length of the particle, because that is largest one. And if I take ratio of this largest dimension to smallest dimension, that would be aspect ratio of that particular particle. The another characteristic associated with particle shape is shape factor. Now in shape factor, if you are able to remember, in the last session somewhere I said the sphere is going to have minimum surface area. Okay, or the to discuss these characteristics we took one example of the, or let's take one additional example. uh, if you allow water molecule to drop from some elevation, so suppose from here one water molecule is going to fall down. So when it starts falling, initially it will have some elongated shape, and when it reaches the earth surface, it will be almost spherical in shape. The reason behind this one is the surface tension of the water will try to minimize the surface area. and minimum surface area will be possible with spherical molecule only. Okay, so if you take examples of other molecules that we have seen over here, the sphere is going to have a smallest surface area, and compared to that sphere, if you take any of the other shape of the particle, let it be irregular, rounded, dendritic, angular, or uh, any shape, all these shapes are going to have large surface area compared to sphere. So the ratio that we are taking, shape factor, that is nothing but the surface area of the particle to the volume of the particle. So if you take sphere and if you take some irregular particle, the sphere is going to have smallest surface area. This other particle will be having some large surface area. If I consider this one A1 and this A2, the A1 is going to be smaller than A2. But if I take both molecules, suppose this is molecule A and this is molecule B, while selecting those two molecules, I took care that the volume of both molecules is same. Okay, I have calculated volume of both the molecules. First one is spherical, another one is irregular. Still, surface area of the sphere is going to be smaller compared to surface area of the irregular molecule. So the ratio shape factor is always going to be, what ratio will be there? Surface area of the particle to the volume. So in case of sphere, the area is always going to be smaller, so this ratio would be always small for sphere, or the smallest value of this shape factor is going to be for sphere only. So there could be a multiple choice question. Identify the particle shape that has got smallest shape factor. So answer is going to be spherical one. Next, size distribution. Now size distribution means, if I take this raw material and starts converting this raw material into powders. So let it be any process, atomization is there, chemical reduction is there, or any process. When you try to convert this raw material into powders, all the molecules are not going to be of same size. So there would be some molecules having a smallest size. There would be some medium size particles, and there would be some coarse particle also. So the distribution between the smallest, the medium size, and the coarse particle, that distribution is nothing but the size distribution. So what is minimum particle diameter? What is maximum particle diameter? Likewise. So that distribution is nothing but the size distribution. Next, there are some other properties that are associated with the particle. The properties are, first one is flow properties. Flow properties means, or what is importance of flow properties is, when you try to push the mixture of that metal powders and additives and all into a mold during compaction. What is compaction? Compaction is offering the shape of the product, right? So when you took metal powders, you added additives, lubricants and all, And when you try to convert that mixture into shape of the product, that process is nothing but the compaction. So when you transfer this mixture into mold to offer the shape, this lubricating or flow properties come into picture. If that flow properties are better, then that compaction process will be better. And if compaction process is better, that distribution of particles and all will be uniform, density will be maximum. And if you increase density, all the properties of materials are going to improve. So that way the flow properties decides the final properties of the product. Similarly, there is one more property that also decides the final characteristics of the product, and that is compressibility. So when you try to convert that powder and additives mixtures into a green product, or when you try to offer that raw shape, this compressibility decides the strength of the product again. More compressible means if compressibility is more, you can increase density of the product. And if density increases, that is going to improve all the mechanical properties. Okay, there is direct relation between density and mechanical properties. If you increase density, going to be improvement in the mechanical properties also. Because why this relation is there? Because if I take a raw metal and if I convert that into powders, okay, so there is a raw metal block and another I have converted that block into powder. Okay, so if I compare density of this one with density of these particles, obviously density of these particles is going to be very less, right? So when you compact it, means when you bring all those particles together, you can increase its density. And as you keep compressing those particles, you will keep increasing density, and that density will start approaching the density of raw material. Initially, the density of these particles will be very less, and when you compress those particles, the density will gradually increase, and that will approach the value of raw material. And when it approaches close to density of raw material, that will have properties of this raw material also, or the properties will also have values equivalent to properties of this raw material. Irfan, turn off your, sorry, RF, turn off your video. RF, just a second. I will throw him out. Where is RF? Manoj, Sheikh Irfan, RF. Okay. So that way there is direct relationship between the density and mechanical properties. Next. Okay. So first step was getting metal powders. We discussed various properties of the metal powders. Now the next step is blending. So why do we need to go for blending? So blending is basically mixing of powder particles all together. Additionally, mixing of powder particles with some other elements like lubricants and some additives. Now, in some cases, even if these lubricants are not there, still this blending is required. Let's take an example. Suppose there are some powder particles of the same material, but some are coarse, some are very fine, some has got medium size. Okay. Now, if I convert this powder into a product, let's consider this square is a product. Now, if I did not take care of the particle distribution. What I mean, if on this end there are large particles, here suppose medium size particle got accumulated over here. On this other end, all the fine particles got accumulated. Okay, so what will happen? As I mentioned, the density is going to decide the properties of material. Okay, now you can easily get that in this corner density will be minimum, right? Because all large particles are there, so there would be a large wide space or free space available in between the particles. Okay, so that way density will be minimum in this corner. In middle region, a moderate density would be there, and in this top region where all the smaller particles are there, density will be maximum. So in the same product, here the properties will be superior. In middle portion, the properties would be somewhat inferior compared to this top portion, and in this bottom portion properties would be poor in nature compared to this top region. So when the part is made from the same raw material, still that properties will not be uniform, and to avoid this one we need to go for blending. So what we do in blending, we try to distribute all sized particles throughout the product. So large particles would be here also, here also, here also, here also, and similarly small and medium particles will be also uniformly distributed. So that way, what the properties that you get across the product will be uniform in nature. Okay, so that is the importance of blending, first reason. Then second, in blending we also add lubricants and additives, additionally some binding materials also. Now all these element that we add to the powders has got some specific roles to play. If I add a lubricant material to these powders, the function is when you compact these powders, or when you transfer these powders and these additional materials into a mold, that transfer should be easy. There has to be minimum friction between mold surface and powders, because that friction is going to impact on the life of the mold. And also, if that friction is minimum, that compaction would be better and density would be better. That is the role that lubricants used to play. If you add some additives, that to improve the basic properties of the material. Suppose I am using aluminium uh, as a raw material, and I want to improve its properties, then I'll add some additional elements to this one. Some additional alloying elements would be added, so that when you convert this into a product, that specific properties would be there. Similarly, binding materials will be added. What binding materials do? When you heat this product, these binding materials will melt, they will form bonds with the powder particles, and they will provide necessary strength to the product. And when you put these elements into the metal powders, again all the elements has to be distributed uniformly, and that distribution will be done using blending. So that is the next step in metal for sorry in powder metal processing, and that is nothing but the blending. So now once you have mixed all these particles and all, the next step will be compacting. So this is all about blending. Next, okay, before compaction, one point is there that we need to discuss: hazards associated with the metal powders. Now, what are the hazards associated with the metal powder? Let me tell you one example. If there are two containers filled with water, okay, both are filled with water. In first container, I dropped a coarse sized sugar, and in another container I converted this sugar into sugar powder by grinding, and then that sugar powder is dropped into this another container. I will ask you simple question. Suppose this is A and this is B. In which container, whether A or B, the sugar dissolution rate will be more, in container A or container B? In A, I have dropped a coarse sugar particles, and in container B, I have dropped a sugar powder. Correct? In case of B, that dissolution rate is going to be more. Now, can any one of you tell me the reason for this one? I need a scientific reason. Why, when I put a coarse particle into water, dissolution takes longer, whereas when I put powder into water, dissolution is going to be more quicker? I just need a reason. Irfan or Akash? You have answered correctly. So I expect a reason for your answer. Yes, Akash, that will happen, but what would be the reason? Due to the size of particle. Okay, Manoj, I need a scientific reason. That's what we are doing, na? We are reducing the particle size. But what exactly happens because of that? Powder dissolves quickly compared to coarse grains. Okay, somebody has typed a lot much over here. Irfan, a given quantity solid dissolves faster when it is ground into small particles, form large, and because exactly, yes. Irfan, have you written by you or you copied it from somewhere? Answer is correct.